Have you ever pondered the immense power held within a nuclear weapon? What if we told you that they operate on the principles of nuclear fission, or in some cases, a combination of fission and fusion? Intriguing, isn't it? The atomic bomb, or nuclear bomb as it's commonly known, is a marvel of human ingenuity, albeit a dangerous one. It's a device that has the power to release an enormous amount of energy, and it does so by manipulating the very building blocks of our universe, the atomic nucleus. Imagine, if you will, splitting these tiny particles or merging them together to unleash a force so great it can level entire cities in a blink. This is no science fiction, but rather the chilling reality we live in. The basic mechanism of nuclear weapons revolves around this concept. So the question arises, how do these cataclysmic devices achieve such an energy release? Let's delve into the mystery. To trigger a nuclear explosion, you need a certain amount of fissile material like uranium-235 or plutonium-239. This is what we call the critical mass. Think of critical mass as the tipping point, the minimum amount of fissile material required to sustain a nuclear chain reaction. It's a bit like a spark that sets off a firework, but on a much grander scale. This critical mass isn't a one-size-fits-all scenario though. It varies depending on the type of fissile material used and the design of the bomb. For instance, the critical mass of uranium-235 is different from that of plutonium-239. The bomb's design also plays a role. Some designs require less material to reach critical mass, others need more. These complexities underline the precision required in the creation of nuclear weapons. It's not just about gathering enough fissile material, but also about crafting the right design. So, we have our critical mass. But how do we initiate the explosion? There are two primary methods to set off a nuclear explosion: implosion and gun type. Diving into the implosion design first, imagine a subcritical mass of fissile material like uranium-235 or plutonium-239. This is encircled by symmetrically arranged conventional explosives. When these explosives detonate, they exert a powerful inward pressure, compressing the fissile material. This compression allows the mass to reach a critical state, triggering a nuclear chain reaction. On the other hand, the gun-type design is a bit different. It involves two separate subcritical masses of fissile material. One of these masses is propelled into the other using conventional explosives. The moment these two masses unite, they attain the critical mass, setting off a nuclear chain reaction. Although these methods are different in their approach, they share a common goal. They aim to reach the critical mass and ignite a nuclear fission chain reaction, resulting in a massive release of energy. Both these methods lead to one thing: a chain reaction of nuclear fission. Once the fissile material reaches the critical mass, a chain reaction of nuclear fission begins, releasing a tremendous amount of energy. This chain reaction is quite the spectacle. Picture dominoes toppling, but instead of plastic pieces falling, it's atomic nuclei splitting apart. Each nucleus that splits releases fast-moving neutrons. These then collide with other nuclei, causing them to split as well and continue the chain reaction. Now imagine all this energy, this heat, this radiation being contained in a space no bigger than a soccer ball. It's like holding a star in your hand. This is the power of a nuclear explosion. But how do we measure this power? We use kilotons or megatons. A kiloton is the equivalent of 1,000 tons of TNT, while a megaton is equivalent to 1,000,000 tons of TNT. The explosive yield of a nuclear bomb depends on its design and the amount of fissile material used. So, what happens when this energy is suddenly released? The explosion generates a massive shockwave, intense heat, and harmful ionizing radiation. The shockwave or blast is a force to be reckoned with. It's like an invisible wall of pressure that obliterates everything in its path, flattening buildings and uprooting trees. Next, we have the intense heat. Imagine for a moment the surface of the sun. Now, think of that heat concentrated into a single point and then unleashed in an instant. That's the kind of heat we're talking about. It's enough to set cities ablaze, causing fires that can rage for days. Then there's the ionizing radiation. This is perhaps the most insidious aspect of a nuclear explosion. It's invisible, silent, but deadly. It can cause immediate sickness, long-term health problems, and even genetic damage that can affect future generations. The detonation of a nuclear weapon is a grave matter with catastrophic consequences. It is therefore heavily regulated and subject to international treaties and agreements.